Welcome guys to a series of videos about slowly time varying electromagnetic field. So in this case we're going to look at induced EMF, which is electromotive force in the electromagnetic scope. So we have this particular classical problem, which is a rectangular loop or wire loop around a solenoid. So pretty much you have let me go here. So you have a solenoid here, which is a circle solenoid, wrapped around or it's wrapped around by a rectangular loop. So there's multiple parts of this problem. I'm just going to show you a picture, a figure of how the problem looks like. So you just have like so pretty much like a rectangle or a circle inside a rectangle, or a script inside a rectangle. So like hopefully by now you're able to understand uh, the fact that in physics you look at geometry, like symmetrical geometry, so and shapes and stuff that give us nice cancellation. So consider the solenoid described. I'm showing you the problem in example 6.5, because I took it, the book that I took it from it's in chapter 6. And assume that the rectangular wire loop of edge length B and C is placed coaxially around it. So it's just as I said, like you have a circle inside a rectangle, and you have B and C bigger than 2A, so you don't cancel the length with the radius. That's just the constraint here. As shown in figure 6.29. The magnetic field due to the induced currents can be neglected. So the magnetic field induced by the current can be neglected. That's a very important part. So if the current inside the rectangular loop can be neglected in this case, so we're just focusing on the solenoid part of the problem. So what's the total induced EMF in the loop? That's the first part. Second part is, so we're just trying to find the induced EMF in the rectangular loop. So when I say loop, we're referring to rectangular part. And second part, we're finding the EMF, which is electromotive force, in the edge Mn, which is pretty much this edge here. And where we at? Okay, so yeah, at the induced EMF at Mn in the following two ways, respectively. So you have to do it in two different ways. First, by integrating along the edge, the induced electric field intensity is vector due to the current in the solenoid winding. So that's just a very complex problem here. Like you're not using geometry here, just using pure integration. The second one is by using that the E induced or electric the EMF, the EM, yeah, we can say EMF at Mn equals to the induced EMF of the triangle OMN, and OMN, this is going to be O, you just write down here before we forget. So this here is O in the center. And going back to it, so the EMF is equal to the triangle OMN, and the computing and then computing this lateral EMF as part of the total EMF from A. So we just break this problem down to its own component. So the first thing here, we're just finding the total induced EMF. Here we're finding total EMF. Forgive me for this shape. And the second part, we're looking at the EMF at MNH. I'm using two forms of calculations. First calculation will be through integration. Second part is will be through using the geometry. Okay. So let's dive to the problem. So first we're going to find the total EMF. This one is pretty much straightforward. So you have E induced equals the negative change in the electromagnetic flux, and that electromagnetic flux equals to the area times the change in, I'll just put it as partial, change of current times your mu, and which is the electromagnetic permeability in space and in the space, which is vacuum, and in the medium. So this is how you find. Oh yeah, we didn't forget the windings, number of turns divided by the length of the solenoid. So this is the equation for the E induced. And in our problem we have, if you go back here, you're not given numbers, just I know you're just giving symbols. I hate that, but like it's just like it tells you like how to think conceptually rather than just like jotting down plain numbers. So so we know the area of this because the rectangular loop is affected by the solenoid here, and the solenoid is a circular, has a circular cross section. So the area will be, which is here, is gonna be pi a squared, because the radius is given as a, not alpha. Alpha is the angle. A is the radius, which is a squared. Go back to it. And that's how we got the pi a squared. Mu is just the mu r times mu naught, which is the electromagnetic permeability through the space and the medium. Because if you think of I have to look at it. Sorry guys. Coaxially, if you think it's coaxially, you have there's air here, or a medium, and there's air in between them. So inside the coil there's a medium, and outside the coil will be some sort of space, which is air. And so another way, let me just write it down in different color here. Let me choose yellow. So you have, let me just fill the question out. 1 second guys. 1 second. Okay, one step. Shuffling the book. I'm just trying to find which one has the space or air permeability, and which one has the medium. So you almost there guys. So mu r actually is the inside, so it has sort of medium inside, and mu naught is the space or the air between the loop and the coil. So going back to it, so we have the mu. I just put mu, and but just few notes here. Mu equals mu r times mu naught. So instead of if we keep writing mu naught to mu r, you just put mu and show something for both of them. And we get pi r squared, and it's just going to be a number of turns per unit of length. That's that. Right there again. And we have air sensitivity to the coil, and of course we have the change in the current, which can change which can produce the change in the magnetic flux, and that's how we find the E induced. So E induced in a nutshell is just a number of turns per length times mu times the area times the change or the derivative of the current. So that's how we do it for the solenoid. Solenoid field is a uniform inside the radius A and 0 outside. You know, 0 outside because there's nothing, there's no medium. And going back to the second part, which is about HMN. Now we're looking at HMN. So, which is this H. So we're not looking at the we're not looking at the total loop anymore, just looking at the HMN. So if you look at it and do the geometry, we have an alpha angle, which is this angle right here. Let me just use the highlighter now. So we have an alpha angle here, and we have this bisector, which is dissect the angle into equals angle, which is alpha over t, alpha over 2, and alpha over 2. So when you have alpha over 2 with this bisector or the with this segment, you get like alpha or tan of alpha over 2 equals tan C over tan inverse C over 2, which is this right here, and divided by tan B over 2, which is this segment here, which is equals to B over 2. So that's how you find alpha. That's for part B, the second part of it, which is just for geometry, is going to be very useful. But now we're going back to the integration. So when you go to integration, you need to find E induced for the EMF will be E induced times the circumference of the loop, which is 2 pi r. In this case, r will be the let me go back here, will be the radius from here to here. That should be r. Then we start it down here. Again with yellow. So we got r, it's this segment here from the origin to the segment. And you can see r length may change because of the angle alpha. Because it's not like straight line, it's not like straight line, it could be straight line, could be at a certain angle, and be a different length. That's why we're going to use integration. So 2 pi r times E induced Mn equals the integration of our favorite formula, which is E induced times dl, and dl will be any dl will be the unit vector, or not necessarily unit vector, but in this case it would be x, because we're integrating over the dx region. So it could be dx dy dz, or dx plus dy plus dz. So it could be a combination of them. But in this case, we're doing like a linear problem. Assuming it's linear. There's one line. It's actually a line. And so now we got E induced times dl, integration by m to the n, E induced times dl cosine theta. Whenever you see a dot product, you assume that you're doing a cosine thing, cosine theta. When you have this cross, which is just like this sign, like over the curve, for example, you're doing sine of theta. But don't worry about this now, because we actually not doing the cross at all in this problem. So don't worry about this right now, we're just doing the dot part. So now we divide both sides of the equation for the E induced Mn by 2 pi r. So you got minus, so we know the E induced, the total E induced dl, we know how much it is. We know it's minus pi mu a squared di over dt. And I believe, okay, yeah, we're forgetting the n over l, n prime. So just like n prime. Okay, the green. Oh, you know what? So again, we're forgetting the n prime. I'm just going to toss it here, just for the record. You know it's not inside the integration. And we have n prime here, which is number of tens per length. And we end up with cosine dx. So after the inside the integration divided by r. So I'll show you now where we plug r inside. So first do the cancellation. Pi with pi, that's gone. So you end up with n minus mu a squared di over dt, all divided by 2, which is comes from the circumference formula 2 pi r. Because why are we using 2 pi r? Again, because we have to assume the cross section of the, or not assuming, the cross section of the coil is this circular, or a circle. So now we end up with cosine theta dx. Okay, that's a bit of a problem, because you have cosine, you have theta changes, but you're differentiating or integrating in terms of x, and you have r also changes, but you're again integrating by x. But we know from our integration table, if you have cosine theta dx over r, you just d theta. And when you integrate total d theta, you get alpha, which is the total angle here, as you can see. So change of theta, or the integration of change of theta is just alpha, or total alpha. And hopefully this so far is very clear. So I know there's a bunch of terms in here, but in nutshell is that what we're doing here is we're just plugging the E induced times dl cosine theta. That's the main part here. The rest is just plugging numbers, plugging the formulas back, doing back substitution. So far we're good. We did this. Now what you do is, alpha over 2, as we said, is 2 tan inverse c over b, because you have like c over 2 divided by b over 2. 2's cancel out, so you end up by c over b. This is a ratio. So like, if you have 2 over 2 is 1, and 1 over 1 is 1, and 1 is half 2, so same thing. Now we get E induced Mn equals minus mu, now we're just doing the final substitution, minus mu. So again we're using alpha back times alpha, so we have minus mu. Okay, I did that here, I forgot the n again, and prime. So we have minus mu over 2, alpha 2 comes from the circumference equation, a squared d over dt times alpha and prime. A big N prime, which is the number of turns per unit length. And we plug back the alpha equation, which is this type, this one here, and we cancel the 2 out, and you end up with this, my formula for the segment. And this is right for any segment. Like N over N for like any like this segment or this segment here. And for this one you have like to consider other, because they're not the same length. So for this you have to consider different, probably like B over C or B or something for the tan inverse. Anyway, so last thing is the formula, which is minus mu a squared d over 2t times tan inverse c over b, again, n prime. Finally, using geometry, which is I like, because with geometry it's very easy. So you just look at this, it's just this arc is what is considered in the induced EMF. So what you do is this E induced equals E induced OMN, which is a triangle OMN. So minus the flux, magnetic flux, and OMN divided by dt. So now we instead of writing OMN, we use alpha angle, and we know that the arc length, which is this arc right here, is going to be alpha in degrees or in radians, so divided by 2 pi. I never forget minus sign, because we have minus in, it's like the E induced is proportional to the negative change in the flux, and that's what we got. And times dq, d magnetic flux, or change the magnetic flux by time, over time, and that should equals to alpha divided by 2 pi E induced, and E induced is nothing but this, right? Okay. This thing here, that's E induced. So negative sign is here also, so we plug it back. So that's why we remove the negative side from the alpha over 2 pi, because if you plug E induced as negative sign, they cancel out, so but you need the negative sign, so that's why I took it out. So that's much it for this problem, and hope you enjoy it, and see you in our next videos about slowly time varying electromagnetic fields. Thank you, and have a good rest of your day.